Hey there, welcome back to Calculus. In this video lecture, we're going to take a look at the material in section 3.5, Implicit Differentiation. You can see the objectives for the video lecture there, and if you looked on the Canvas page, you'll see that there's actually more learning objectives for this section there. I'm just going to do two of them in this video, and then the other two in a second video, trying to keep the video shorter and easier to focus on. All right, so in this one, what I want to do is just tell you what I mean by the difference between something given explicitly and implicitly. So when a curve is defined explicitly, y is a function of x, versus implicitly by some equation in x and y. And then the whole point of the section, this implicit differentiation, is to show you how to find the derivative dy dx even when a curve is given implicitly. All right, so it's a very powerful technique that I suggest that you try to learn well, because it can make some problems that are explicitly very algebraically difficult to do. They can be much easier to do if you do them implicitly. Okay, so let's just get going here. Let me tell you, first of all, what do I mean by explicit versus implicit? Well, so in all cases, I'm talking about a curve in the xy plane, so a relationship between the variables x and y. And that relationship is so-called explicit, and this is what you're most used to, if the equation can be solved for y only in terms of x, yeah? So an explicit function relationship is when we've solved for y in terms of x. That's most of the kind of functions that we think about, right? Y equals x squared, y equals sine x, y equals 2x plus 5. The whole point is that the right-hand side of the equation doesn't have anything but constants and the variable x in it. So that we've explicitly, quote unquote, said what y is in terms of x. Implicitly, on the other hand, is we just have some equation that has x's and y's in it. So that's all I mean by this function notation. Capital of f of xy, just think of it, it's some expression that has x's and y's in it. And that expression is equal to some constant. Sometimes that constant's 0, sometimes it's not 0. So it's an equation that relates x and y, but we haven't solved for y in terms of x, and we haven't solved for x in terms of y. So when people are talking about a curve given that way, they talk about y being implicitly a function of x. So we haven't got an explicit formula for it, but rather some equation that defines the function. All right, let's look at an example. Let's look at an example down here. What have I got? I've got an equation. Let me highlight it here so you're looking in the same place I am. I've got an x squared plus y squared is 25. So that equation defines y implicitly as a function of x. If you like, I'm not going to write it here, but your x squared plus y squared, that's my capital F of xy. And what's the constant? Well, the constant is 25. Yeah, so that yellow highlighted equation has this form. It says some expression in x's and y's is equal to a constant. And it defines y implicitly as a function of x, in the sense that this equation has some graph. Maybe you could pause for a second here. Do you know what the graph of that equation is? I want you to. I'm going to show it to you in a second here, but that equation has some graph, and that graph is not necessarily globally a function, y is a function of x, but along a little piece of it, any little piece of it, it is. In this particular example, this equation isn't so complicated. We could solve that equation for y. Yeah, what would we do? We'd have to subtract x squared from both sides and then take a square root. And when you take a square root, well, there's two possible values for it, a positive and a negative square root. So this implicit equation actually defines two functions. One of them I've called f of x, the positive square root of 25 minus x squared. The other one I'm calling g of x. It's the opposite of that. It's negative the square root of 25 minus x squared. Yeah, so two different implicit functions are determined by that equation, f of xy is equal to 25. And let's look at some graphs. Yeah, when I asked you what the equation of x squared plus y squared equals 25, did you say it's a circle? It's a circle with center at 0, 0, and its radius is 5. Yeah, it's the square root of that. Come to an office hour and talk to me about that if you want to talk about equations of circles. But you can look at this equation of this circle. That's certainly not a function of x globally, right? Because if you pick an x value, it fails the vertical line test. There are two different points on this curve with the same x value, and functions can't do that. But when we solved for y, when we took the positive square root, our f of x, the positive square root means we're only taking the y values. So that upper semicircle is a function of x. And likewise, the graph of g of x over here is the lower semicircle. That's also a function of x. All right. So if I wanted to ask questions about calculus of such a curve, like maybe if I want to pick a point right here and ask, like, what's the slope of the tangent line? Well, I could do that with the calculus I already know because that point is on the graph of f. I've got a formula for f, so I could use calculus to find the equation of that tangent line. If you wanted to give me a point down here and ask me what's the equation of the tangent line of that point, well, I'd use the function g. I'd use the calculus, take the derivative of g using the chain rule, yeah, to find the slope of those tangent lines. But in this section, I want to show you a technique that it's not necessary to have these explicit functions if you just want to answer a question like, what's the slope of that line? You can do it right from this form. That's what implicit differentiation is. Okay. Before we get involved in the differentiation, let me just show you that sometimes there are some curves. This is a very interesting curve. It's called the folium of Descartes, after René Descartes, the inventor of our XY coordinate system. Our XY coordinate system is sometimes called the Cartesian coordinate system after René Descartes. But I'm looking at this equation, x cubed plus y cubed is equal to 6xy. It defines a curve in the plane. It's not really my focus here of how to graph this. I had a computer draw it by plotting points, but that curve looks like this. It's a very interesting looking kind of loopy-loop curve. It certainly does not define y as a function of x. It fails the vertical line test miserably. Some values of x have up to 3y coordinates that go with them. But unlike our circle example above, it's difficult for me, maybe even impossible, to solve this equation for y. Yeah, anytime you try to isolate this y, maybe you take the x cubed over to the other side, but there's a y over here. And if you try to get that y on this side by dividing by it, well, then you've divided the x cubed term by y. So you have to do some pretty tricky stuff to solve that thing for y. But still, locally, y is a function of x. What do I mean by that? If you pick any point on this curve and you restricted yourself to just a little piece of it, only look at the part that I'm highlighting with the laser pointer, then that does pass the vertical line test. Yeah, no matter what point on the curve you pick, if you stay close by that point, then it does define a function. Yeah, even if you pick a point like this, you could think it's on that function or this one. Yeah. So locally, y is a function of x. If you want to see graphs of those functions, I can't squeeze all of this on the same screen, but here you've got the folium of Descartes on the left, and then the author of our textbook is showing us three functions of x. Each one of those three graphs does pass the vertical line test, and the union of those three graphs put back together would give us this folium of Descartes. Right? So the idea is, well, or the question is, how can we find tangent slopes when we don't know this formula? I said this f of x is difficult to define. Yeah, well, that's the good news. The good news is that you don't need to know f of x explicitly if you just want to know the slope dy dx. As long as it's true that y locally is a function of x, we can treat it like that without knowing what that function is explicitly and still be able to solve for its derivative, right? So it's kind of a nice technique. Okay, so that's all the motivation. Now let's get down to it and look at a specific example. I want to start with our circle. So I would like to find the slope dy dx for the curve that's defined by the equation x squared plus y squared equals 25. Okay, so I'm looking at this curve, x squared plus y squared equals 25. I'd like to find its slope, and I don't want to solve for y. So here's the main idea. The main idea is to differentiate with respect to x, treat y like an inside function. Y is an inside function. What do I mean by that? Let's take this equation, x squared plus y squared equals 25, and let's differentiate both sides of it with respect to x. So I'm going to write the derivative with respect to x of the left-hand side is equal to the derivative with respect to x of the right-hand side. So I'm differentiating both sides of that equation with respect to x. And on the left-hand side, we have a sum. And our sum rule for derivatives says that the derivative of a sum is the sum of the derivatives. So I'm going to take the derivative of x squared and the derivative of y squared separately. The right-hand side's a constant. The derivative of a constant is 0. Right? And now, continuing along, let me give myself some room here. The derivative with respect to x of x squared is 2x. Yeah. Now, the derivative of y squared with respect to x, remember, we're treating y like it's an inside function. So this is a chain rule problem. So the outside function in this particular example is the squaring function. So the derivative of the squaring function is 2 times the thing to the first power. But then by the chain rule, I have to multiply by the derivative of y with respect to x. And I don't know the explicit function y in terms of x, so the best I can do is write this for its derivative, dy dx. You can also write y prime if it's easier, right? And then that's equal to 0. And then we can solve this equation for dy dx. Yeah, what would you do? You'd subtract 2x from both sides, I believe, would be the first algebraic step. And then divide both sides by 2y. Certainly that has to be the case that y isn't 0, but we'll just do it, writing that down over here. As long as y is not 0, that's a valid computation. And here I'm going to clean this up a little bit. Dy dx is minus x over y. And that's my final answer. Right? So what did we do? It's kind of a neat trick. We found the derivative dy dx without ever explicitly knowing y as a function of x. It's cool. However, the downside is, or it's not a downside, but it's different. Our answer is in terms of both x and y. So when the function y equals f of x is given explicitly, then the derivative y prime is explicit in terms of x. But here, the derivative is going to depend on both variables. Yeah, so you have to get used to that. That then when you take the derivative of something implicitly, what we just did is called implicit differentiation. The answer, the dy dx expression, will in general involve both x and y, and that's okay. Because if you gave me a point on that curve and you wanted me to tell you what the slope was at that point, well, as long as I know both x and y coordinates of the point, then I can tell you what that slope is. Cool. Like here. Let's try it right now. Maybe I can leave that in view. Maybe somebody wanted me, I'm circling back through some ideas, to find the equation of the tangent line to this circle, x squared plus y squared equals 25, at this point, 3, 4. Yeah, you can check check that point's on the graph. 3 squared is 9, 4 squared is 16, and 9 plus 16 is 25. So 3, 4 is on that circle of radius 5. And maybe you could see that it's the hypotenuse of a 3, 4, 5 right triangle, 5 being the radius, right? And I want to know what the equation of the tangent line is. All right, well, to find the equation of a tangent line, you need a point. Well, we know the point. It's 3, 4. We need the slope. The slope of a tangent line is the derivative, dy dx. And here, I'm going to take that formula that's at the top of the screen, minus x over y, and I'm going to replace x with 3 and y with 4. So my slope there is negative 3/4, pardon me. So we were asked for the equation of the tangent line, so I'm going to do it in point slope form. I'll write y minus 4 is minus 3/4 times the quantity x minus 3. And you can leave it like that if you want to, or if you want to get y equals, if you put it in y equals mx plus b form. I think for purposes of keeping this video short, I'm going to take this as my answer. I'll just leave it in point slope form. So that's the tangent line to the circle x squared plus y squared equals 25 at the point 3, 4. And if you want to choose some other point, like, let's pick one down here real quick. What point is on the very bottom of the circle there? The x coordinate is 0. Since the radius is 5, but that's a negative y coordinate, that's the point 0, minus 5. What would this tangent slope be at such a point? Geometrically, you can see it in the picture, I think, that the tangent slope at that point is 0. Yeah, that's a horizontal line through there. This formula confirms that. If x is 0 and y is minus 5, this is minus 0 over 5. That's 0. Nice. Cool. I'm going to leave it to you, but just to throw it out there, what about a point like this? What about a point minus 5 comma 0? What does this expression tell us that the slope is there? We'll talk about that more in the second part of this video lecture, but I think for right now, I'm just going to kind of throw that out as a intriguing statement that I hope you'll think about. Cool. All right, let's keep going. The thing I'd like to do next is flex the power of this a little more. I'd like to find the slope at any point on this folium of Descartes. Yeah, I can't solve this thing for y in terms of x, so this implicit differentiation method is really the only way we have to do this. So let's try it again. So we're going to implicitly differentiate this thing. We're going to differentiate both sides with respect to x. So I'm going to take the derivative with respect to x of x cubed plus y cubed. I'm going to take the derivative with respect to x of the right-hand side, 6xy. Okay, on the left-hand side, same kind of phenomenon as before. We have to take the derivative of the sum. So we do that by taking the sum of the derivatives. So we'll take the derivative with respect to x of x cubed and the derivative with respect to x of y cubed separately. On the right-hand side, I've got a constant multiple 6. So that 6 can certainly come out through the derivative. Okay, so I'm just trying to put in lots of little steps here. Now let's start differentiating. So the derivative with respect to x of x cubed is 3x squared. The y term I have to treat like an inside function, right? Because I'm taking the derivative with respect to x. That's why I'm using the Leibniz notation here to remind you of that. So y is an inside function. So the outside function here is the cubing function. So the derivative of the cubing function is 3 times the square, but then I have to multiply by dy dx by the chain rule, right? Because I'm doing this implicitly. Y is implicitly a function of x. So this is by the chain rule. Stop the video right there and kind of think about it for a second, or make a note to ask me a question if it's not clear. On the right-hand side, I'm differentiating x times y. Well, I have to do that as a product. X times y is a product, and y is a function of x, so I have to treat it accordingly. So using the product rule, I have to take x times the derivative of y with respect to x, and then I have to add to it the derivative of x, which is 1, times y undifferentiated. Okay? So now it's an algebra problem. We need to solve this thing for dy dx. I see a dy dx right there and a dy dx right there. So I'm going to multiply everything out and bring my dy dx terms over to one side. So maybe it's better if I just do that without trying to talk while I do it. But if there's nothing actually to do on this side. On the other side, I'm just going to distribute my 6. So I get 6x dy dx plus 6 times y. Okay, and then this will always be the case, even though these things might look a little bit busy, it's always going to be the case that when you're done differentiating, some of your terms don't have a dy dx in them. Some of your terms do have a dy dx in them. Terms, remember, are separated by pluses and minuses. So you bring the dy dx terms to one side and the non-dy dx terms to the other. So that's how you're going to organize this algebra. So I'm going to bring the underline in blue terms over to the left. So I've got a 3y squared dy dx is already over there, and I'm going to subtract 6x dy dx. Okay, I'm taking the underlined in red, the non-dy dx terms to the right. 6y was already over there, and I have to subtract 3x squared. All right, once you've separated them like that, then you can factor dy dx out of the left-hand side, or whichever side you put it on. That's why we separated the terms. Okay, the last step is just to divide. So dy dx is the quantity 6y minus 3x squared over 3y squared minus 6x. Yeah, and if you want, everything there is divisible by 3. We could sort of simplify this a little bit if you want to. We could write this as 2y minus x squared, all divided by y squared minus 2x, dividing out the common factor of 3. So here's my answer. The question was find dy dx for points on this folium of Descartes, and the slope at any point xy is given by that rational function. And again, notice that it's in terms of both x and y. It'll always be the case, and not always, but it's not forbidden. When you differentiate something implicitly, then your answer is going to be in terms of x and y. All right. I think I'm not going to do it to keep the video short here. You can look in your book if you like. It's an interesting question. What are some points on this graph? 0, 0 is one of them. I'm just going to leave it to you to check that 3, 3 satisfies that equation. If you let x and y both be 3, then you get a point that's it's actually out there on the tip of that loop right there. And it satisfies the equation. 3 cubed is 27. And 27 plus 27 is 54. And 54 is equal to 6 times 3 times 3. So 3, 3 satisfies it. So real quickly, let's just ask the question, not a whole tangent line, but what's the slope at the point 3, 3? Just to illustrate what you do with this thing over here. Well, you let x be 3 and y be 3, and it tells you the slope. Let me introduce some notation that we'll use throughout this course while we do this. It's called an evaluation bar. So it's kind of a way to write. The way you read this is the derivative dy dx evaluated at 3, 3. Yeah, so that vertical bar with that little point down there means I'm going to take the derivative expression and plug in 3 for y and 3 for x. So 2 times 3 is 6, and 3 squared is 9. So the numerator is 6 minus 9. The denominator is 9 minus 6. Yeah, and 6 minus 9 is minus 3. The 9 minus 6 is 3, and that ratio is going to be -1. So the slope is -1 at that point. Sorry for all the scrolling, but it's the only picture I have. I don't know if that answer is correct or not. I mean, I do think it's correct, but I don't know it. I have to verify it. But I just want to point out that in this picture, it certainly looks like whatever the tangent slope there is, it's negative. That the slope of that line should be negative, and its slope is in -1. We just calculated it. Cool. Okay, let's keep going. I'm going to just do one more example in this video and try to keep it short, and then we'll pick up another video where I'll talk about some applications of looking for certain kinds of tangent lines, differentiating implicitly, and I also want to show you that implicit differentiation can be used to find derivatives of inverse functions. That's the next video. So in this last one, I want to illustrate to you what it's like to calculate a second derivative when something is given implicitly. All right, so keep your eye on this. I want y double prime. And I'm writing it in the prime notation, not for any particular reason. It's a little bit easier on the eye than the Leibniz notation for second derivatives. D squared y dx squared is how Leibniz notation writes that. So I want the second derivative for this first example, so we can recycle a little bit. So I'm not gonna do it again, but recall from above that we already calculated the first derivative. This was the first thing we did. The first derivative, y prime or dy dx for that circle was minus x over y, okay? So when you do something implicitly then, well, just like always, the second derivative is the derivative of the first derivative. So that's all I'm writing is y prime prime is the derivative d by dx of my first derivative, minus x over y. Yeah, and then let's sort of walk through the computations here together. First of all, there's a minus sign here, and I'm going to put that minus sign in front. It's a constant. It can come through the differentiation. So here's that minus sign. And then what am I differentiating? A quotient, x over y. So I got to use the quotient rule. So let's just walk through the computation together. So what am I doing? I'm taking my denominator and squaring it. That's how the quotient rule starts. And then it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, right? Good. So that's y, derivative of x with respect to x is 1 minus x. And then for the dy dx, you could write dy dx here. I just decided to write y prime. It's easier for notationally. So I just, because I don't know y explicitly as a function of x, so anytime I have its derivative, I just write y prime. Okay, So you can check the algebra, pause it. But now I can't leave the answer like this. I said it's okay for the answer to be in terms of x and y, but this y prime has to go. I can't leave the answer in terms of y prime. It only can have x's and y's in it as variables. But it's no problem because y prime is minus x over y. We know that. So I just substituted it. So maybe it'll help if I color code it. This y prime, I'm just replacing it with its value in terms of x and y. It's minus x over y. Yeah. And then the rest of this computation is just some algebra. Maybe I can just be quiet and let you enjoy it here. But all I did is, I did minus a minus is plus in that step. So I have plus x squared over y. And then what did I do? I just rewrote the division by y squared as multiplication by a reciprocal. So here's my y plus x squared over y. Then I got a common denominator. That common denominator would be y, and I multiplied through, or excuse me, no, I just multiplied through by y squared. I don't know why I'm trying to talk you through this. You can just check it out yourself. I multiplied through by y squared, canceling using rules of exponents, and then I got a common denominator. It's y cubed. So I had to multiply this term by y squared over y squared. That leaves me at this expression. And then here I'm actually just kind of playing around, but it's interesting to do it that if you factor out this minus sign here, you get minus x squared plus y squared as a quantity. But on this curve, x squared plus y squared is 25. So this final version is the simplest I can write that second derivative, minus 25 over y cubed. Cool. Okay. Well, that's it for part one of this video. You can digest this stuff, try some of the calculations on the activity and the homework if you want, and then come back and watch the video where we'll talk about how to use implicit differentiation to locate horizontal and vertical tangent lines and take the derivatives of inverse trig functions. So thanks for listening.